Okay, do we know how to turn off the audio over here?
Turn off?
Turn off the audio. I don't want the audio coming out.
Oh.
Hello. Okay, cool. It didn't do it. Hey everyone, thank you so much for coming to our AI Cyber Symposium. Woo! Yeah, so the symposium is a fun thing that cyber and AI like to do together every quarter, since we're close clubs and we value our relationships. But also we really want to celebrate all of you to show off all of your cool project and hard work that you've been putting in throughout the quarter. Yeah, so thanks for attending again. Cyber would like to thank a lot of our experts that have helped with our club. We have professors who have been project mentors, guest speakers, alumni advisors, and just good faculty from UCLA.
Yeah, so we'll give a brief introduction. If you don't already know, ACM AI, we're the largest machine learning club here on campus. We do a lot of things from our workshops. We do a capstone track for beginners and then a research track if you're interested in learning about more advanced topics like diffusion and reinforcement learning. And we also do our projects track, which is our quarter-long projects, and you'll hear from all of our projects this quarter today.
Yeah, and then ACM Cyber, we are also the largest club in our field. We're actually the only cybersecurity club on campus, so we're pretty cool. We do three main things. We do Cyber Academy, where we teach basics concepts about cybersecurity, and we do this through hands-on learning because we think that is the most fun way to learn. We also have Cyber Lab, which works on a quarter-long project. You will get to hear from Cyber Lab about the cool projects that they have been working on. And lastly, we have PBR, or Psi Beta Rho. This is our competitive CTF team that is pretty good. Yeah, so what did we do? This is just a rough agenda of how the symposium will go. We'll alternate between ACM AI and ACM Cyber presenting. And then in the middle, we will have intermission for dinner. And then we'll go back to presenting all our stuff again. So yeah, I'd like to welcome Kit Lab down here to present. And also just a reminder to presenters, since we are recording this, if you are talking, please make sure to stand in front of this computer so we can catch your audio.
All right, so this is Rootkit Lab. The goal of this was basically to understand how rootkits work, especially at the kernel level. So we experimented with writing rootkits targeting Linux. And yeah, I'll let some people present kind of how we did that.
So the first thing is, what is actually a rootkit? Essentially, it's just a set of tools or code to hide an attacker's presence on a system. Like, say, example, I am an attacker and I want to go onto someone's system and I need to do this discreetly. We can do this using a rootkit. We essentially want to hide files, processes, and network systems when we do this in order to evade detection and persist as long as possible on someone else's computer. This was done on the kernel mode, which is essentially a privilege mode on someone's computer. And this lets us gain access to the OS and gain access to a system's hardware and memory. We essentially, during our rootkit lab, we created a driver to get us into the kernel to gain privileges, execute code, and with the permissions that we need.
Yeah, so I guess a distinction that we are going to maybe commonly refer to in this presentation is the difference between kernel space and user space. So user space is basically what the user you are interfacing with, like most of the time, with all like the application code you're running, that runs on user space, basically. And kernel space, as we see, as Alyssa mentioned before, is basically a privileged space where basically they get access to like direct access to hardware, and user space code is limited. Has limited privileges, so it needs to communicate to the kernel via syscalls in order to sort of get like services from the kernel.
So we started out by hiding processes in user space on Linux, and they're generally speaking, those process managers or process viewers like PS or top or whatever, they read from this directory called proc. Proc contains a ton of files that contain PIDs, which are just numbers or identifiers attached to each process. Generally, programs like PS, they read this directory using libc's readdir function. But what we can do is that if we have control over the user space environment and can say preload a library of our own, what we can do is we can clobber libc reader with our own, which basically just reads the PIDs that are being passed through it, and we'll toss out the ones that we want to keep hidden. And since preloading in an environment generally takes higher precedence over like other libraries, it generally means that our clobber runs before libc's.
All right, so we started off by creating like a simple user space rootkit that hides itself by clobbering the libc, right? But we can do better than that because like clobbering a libc is not like always like it's not that like not obvious and it's like not always possible. So we can do better than user space. So we're moving into the kernel. So we can avoid this. And then so what we did is to create a loadable kernel module in Linux that loads into the kernel and interacts with our code, or it hides itself by overwriting a like iterate shared function in this particular struct called like proc root operations. So the way like processes are like detected in PS is that there is this like mounted file system on Linux called like the process file system. And so there's this particular struct called like proc root operations that's used when you're iterating through the like file directory entries for that particular process file system, and we like do something to that struct, like basically override it, right, in order to hide our process. Yeah, and then we use like these headers to be able to like interact with the symbols and stuff.
So this is more on process hiding. So we basically hijack the function that iterates over /proc and make it skip our malicious processes.
Yeah, so if you look at the code, so like this is the function that's get called for each directory that you iterate over. We check if the name is like a number. If it's a number, then like we check if that's like the process ID that we want to hide. And then if it is one that we want to hide, we just like skip over it. And otherwise, we just call the original function so that it will just continue iterating normally.
Now we've hidden it. So what now? Since the file is hidden from the directory, it's we can't call PS to find it, but there's still some way to find it. Since if we're given that a PID count is really low, we can just brute force it because we can just iterate through every single PID, check it and check if it exists. If it exists and it's not in the readdir in the proc directory, then we know it's trying to hide.
Yeah, so the way we do this is using kill, which is a syscall for sending signals, except if we pass in the argument 0, then it doesn't actually send the signal, but it still does like the checking if the process exists. So we can use that, and then like it'll return like 0 if the process does exist. So we just check that, and then yeah, we can find it.
So now we're moving on to portable hijacking. So LKM depends on a specific kernel version and config, so it's not portable. So we are presented with a common exploit primitive, which is our read write into physical memory. And we want to take physical memory control and translate that into code execution with KASLR in place. And so we'll talk about the code.
Oh, okay, sure. So on like x86 specifically, there's a thing called the interrupt descriptor table, which is how like processor interrupts are handled. So this is used for like transitions into kernel space and all sorts of things. And it's needs to be basically there's a table of memory with a ton of kernel functions that it'll jump to on the thing on an interrupt. So one way to sort of like when we have physical memory control, we want to first find virtual memory and then or the virtual address of the kernel because it's randomized, and then find a translation to physical memory, which is pretty easy because its physical memory is low, right? Like usually only a few gigs or something like that. So we can basically scan memory for predictable IDT tables. There were pictures in here. I don't know what happened to them. But yeah. Anyways, this also gives us a way to sort of hijack the code because when the IDT is, if we can overwrite the IDT, it'll jump to our code. So the general idea is that in everything is like page aligned. So there's going to be a lot of pages that have remainders that are all zeroed and aren't used by the kernel. We can then write to those pages our own code, and that's called like a code cave because it's sort of unused executable memory. And we can collaborate no issue. We write some code that extracts various information, like there's model-specific registers in x86 that have all these addresses. Run our code, write it back to physical memory, read it back, and then now we have all the information we need. And then the end goal is to sort of hook the syscall function, which in modern Linux is just a giant switch statement, so you can like easily pattern match it and then just overwrite each relative jump because you have all the information. Yeah, that's like sort of a common scenario when you want to make this apply to any kernel without having to like load a driver, because that's, obviously really easy to close off on a system that is like secure. So. Yeah, that's I think that's it.
Hello, everyone. We're presenting Atari Surround. I'm Leon.
And it's Julian.
I'm Oliver. I'm James.
I'm also Leon.
And we'll let the project's members present what they did this quarter.
Okay, so RL is concerned with how like an intelligent agent should take actors my fault. To take actions in a dynamic environment in order to maximize reward or signal. And it's like used in like LLMs like ChatGPT, robots, and like drones and like game AI. Yeah. Okay, so instead of going straight into Atari, we first started with like Lunar Lander, which is a simplified game where it's just getting a lunar lander to land in like the proper area with like left and right, which is simpler than just Atari itself, or Atari Surround. And we didn't actually see the game, we actually just got like these values and we just figured out like how to make our algorithm better from that. And it says we use the reinforced algorithm in this, but we quickly switched to DQNs, which we'll explain later.
Okay, so what is Atari Surround? So you can basically think of it as like an 80s version of the game Snake.io, if you ever played that game before. Basically, there's two players, each controlling like a little character that leaves a trail behind it, and the goal is basically to like trap the other player, make sure that they can't like move anymore. If they run into your wall, they die. If they run into their own, they die. So you basically have like in terms of like machine learning, you basically have two agents that are in a single environment, and since we're doing reinforcement learning, we got to figure out how to reward our agent. So things such as like how long the agent survives for, we want to increase that because then it'll get our agent to like produce better results, as well as maybe like also like the length of the path. Yeah, so that's basically Atari Surround. And actually, um, like like I mentioned, we actually started with reinforce, which is a policy gradient algorithm. A policy is basically just like a way of mapping whatever the environment is, which is in Atari, like the state of the game, into a probability distribution of actions that the agent can take. So basically what that means is like the agent gets a set list of things that they can do in the game, and then the policy tells the agent, okay, you have like a 10% chance to do this, a 20% chance to do something else. And the reason we do this policy is because it's like a lot it's easier to implement because of how simple reinforce is, as just like you can think reinforce is a very like old kind of simplified version of what we have nowadays in more modern algorithms such as DQN, which we'll get to that later. And we use neural networks to learn this policy. And you can see this very complicated math expression up there. That's the reinforced algorithm in a nutshell. The only thing that really matters, or basically like to sum it up, is basically saying reinforce really cares about what the agent did, like the most recent action that the agent took. So whatever the most recent thing that they did, we want to like heavily favor that. And anything they did like 10 states ago or like 100 states ago, we don't really care about, but we still want to take it into account. So we're just going to discount whatever happened in the past and weigh what happened like in the present a lot more. And we use gradient descent to update the weights of the policy.
All right. So what did really worked really well was DQN or Deep Q networks. So DQN is an off-policy learning method, which is in contrast with the on-policy reinforced that we talked about earlier. So DQN learns the expected sum of rewards for each state action pair. So the advantages of this include sample efficiency because we are using an experienced replay buffer to make better use of the data instead of only learning from a few trajectories with the on-policy method. It also leads to better convergence because reinforced, as mentioned earlier, can suffer from slow convergence due to high variance in gradient estimates because we are only learning the current policy instead of the reward function. So some techniques we use to improve the DQN include a prioritized experience replay buffer to prioritize the most recent experiences because they're most relevant. And also we freeze the target network so that we only update the neural network for Q after K iterations to mitigate the problem of chasing a moving target. Yeah, so that's all we have. Thank you.
Any questions?
Yeah. Sure, yeah. I was just curious, why did you guys use a hard update for the target network instead of soft update? Or did you guys have a soft update?
We did try both. Yeah, so we have an option in our code to toggle it on and off.
And hard update works better.
Soft update works slightly better. Yeah, it's a bit smoother than the hard.
Or actually, like with soft updates, it seemed a little bit more finicky in practice. And you kind of see key value explosions a little bit more often if you don't like tune it just right. So I think hard updates, like even though you can suffer the problem of maybe like freezing it for too long, it seemed to be more like consistently decent. But like both in theory should work.
You try doing something like PPO, like something more modern.
We did not get there.
That's too complicated. It's like a lot of work to implement.
All right, I guess we can just talk about our lab. So this is the XSS sanitizer lab. Just names, I'm Alec.
I'm Daniel.
I'm Kyle.
I'm Jason. I'm Chris.
I'm Sophia.
Hanson. Ryan.
All right, background.
Yeah, so cross-site scripting or XSS is a web vulnerability that allows code injections to be run, which causes JavaScript to be run when a user visits a given site, and it could potentially steal data or run unauthorized scripts. There's different types of XSS. One is a reflected XSS, which happens when a user clicks a link, and another one is stored XSS, which happens when a user visits a web page.
DOM-based XSS is when you exploit vulnerabilities in the website's JavaScript code to inject malicious scripts. And you can sanitize these attacks by removing any harmful tags and attributes from the HTML. And this happens on the browser of the person rendering the input.
Okay, so there are two ways you can implement the basic sanitization. So you can use a whitelist or a blacklist. A blacklist is a list of tags that you will want to remove in the sanitizing process. So things like on error can give like malicious code. A whitelist is a list of tags that you want to allow, and it sanitizes everything else. One con about the whitelist is that you have to include all the tags that you want to allow, so it can be quite lengthy, but generally it's better than a blacklist because the worst case scenario for a whitelist is that you remove some harmless code, but for a blacklist, the worst case scenario is that you miss malicious code. And we decided to take our whitelist from the DOM Purify open source code.
So the way that we sanitize the code is that first we have to process the inputs. The inputs is basically an HTML page, and we have to use the parse from string function to parse it into a DOM tree structure so that we could like actually
loop through the tree and then check whether it's in whitelist or not. And then we use a recursive function to loop through the DOM tree and check if the tag name is inside the whitelist. And if it's included, then we check for the attributes, whether the attributes is malicious or not. If the attributes is malicious, then we will sanitize it, basically just remove it. Yeah, these two photos are the way, this is the DOM tree and this is the way how we, the original HTML page, and then using parsing string, we turn it into a DOM tree.
Alright, as we can talk a little bit about the testing. So essentially we created a test suite where we could just give it like a big list of test cases and it would go ahead and try and run those test cases by just rendering it in a tester, like a tester page. And what would happen is if no JavaScript runs, then our sanitizer worked because it got rid of any scripts that attempted to run. But if any code ran, then we know our sanitization failed. Anything else?
So the way we detect events is we see if alert gets called by our code, and if it is, then it failed our test case, and then we highlight that test case red. So here are some examples of test cases. So the first three pass because all the tags and attributes are in our whitelist. But the fourth one, all those tags and attributes are in the whitelist, but it still fails the test case. So this test case is an example of MXSS, which will be talked about in the next slide. Yeah, so MXSS is like a special kind of XSS attack that takes advantage of how web browsers parse HTML. So when a web browser parses HTML and it encounters some kind of error, it'll typically try to fix the error so that the content can be displayed. So like, for example, if there's like a missing closing tag, it'll try to insert the closing tag. And this can cause like the HTML to change before and after it's parsed. So the vulnerability here comes from hiding malicious code in like malformed HTML. And by doing this, it can bypass our like the first parse that's done by our sanitizer, so it doesn't see the malicious payload. But then when the parser returns the HTML and it's parsed by the browser, it suddenly activates and the payload essentially bypasses our sanitizer that way. And these kinds of attacks are really hard to detect. One notable example is when Google search was actually subject to an MXSS attack in 2019. So the way we deal with it is quite simple. We just parse and reparse the HTML over and over again until it stops changing. And that way we know that there won't be any like unforeseen like mutations when the web browser parses it.
Yeah. And this image is like the rendered version of the test that failed our test suite. This is a real exploit that bypassed Purify. On the top left over there, you can see the first parse. The image src on error is in a style tag, so it's treated as plain text, and our sanitizer thinks this is fine, it's not actually malicious. But then on a reparse, magically the image pops out away from the style tag down here, so it becomes an actual vulnerability. This is the mutation in the mutation XSS. Yeah, that's it for our presentation.
All right. So our project was building a vision language model. So we wanted to understand how to like the different parts in a vision language model with the vision encoder and the text encoder. And then we trained it and fine-tuned it on different data sets that we found on Kaggle and Hugging Face.
So a vision language model is basically like a combination of computer vision and natural language processing. It has two key components to it. It has the language encoder and the vision encoder. The language encoder is basically turns text into text embeddings by using transformer, and vision encoder it turns image into vector embeddings. And most VLM uses vision transformer for this. And vision transformer is basically like a transformer but for image. It turns it image into like smaller patches and treat each one as an individual token. And the model would take the data from the language encoder and the vision encoder, combine it, and kind of just learn to associate the text and image. Some applications of VLM is like image captioning, text to image search, and like answering visual questions. Contrastive learning is like a technique in machine learning where the goal is to just group similar items together and kind of separate the not so similar items. And one application is CLIP, the contrastive language image pre-training. It takes the image, put it into the image encoder to get the vector embedding, takes the text, put it into text encoder to get the text embedding, and kind of use dot product to create the similarity matrix. And the goal is to maximize the diagonal elements of the similarity matrix and to minimize the off-diagonal elements because we assume that image one and text one is supposed to go together, and image two and text two is supposed to go together. So it should have like high similarity. And during the training stage, we use the contrastive loss function to measure like how well the model is learning.
Oh yeah, okay. And then another extension that we looked at was the mixture of experts model in the decoder. So we're just gonna I'll just explain this on a high level. So basically, in the transformer, in the transformer block, there's gonna be the multi-head self-attention and then also the feed-forward network. But in this case, you would just replace the feed-forward network with like kind of itself, but like multiple times. So basically, you replace it with like n experts, and then you use the noisy like top K routing. So basically, this means that like if you have, for example, 8 experts, and then you use top 2, then you would feed the token to like the top 2 experts. So like each expert has the same structure as the feed forward network. You would input the embedding. You would take it to a hidden dimension of 4 times like the embedding dimension, and then you would map it back to the output. So like you would just use like a linear layer to determine like which experts get like the are fed like the embedding. And then but like the high level benefit is that like the mixture of experts can have like lots of parameters, but like it has sparse activation, so this allows for like more efficient computation because you're only activating like a small like subset of the total number of experts. And then this also like in turn allows the different experts to like specialize different types of inputs, therefore like increasing the flexibility and generalizability of the decoder. So really quickly, just like putting it all together. Also the decoder is used for like auto-regressive like text generation. So like given an image, like you would generate like captions based on that. But basically the decoder would consist of like you would take in embeddings from the encoder, and then you would have like several sparse MOE blocks that utilize like the multi-head attention and then the experts, and then like finally you would be able to like map these outputs to the like vocabulary distribution. So like you would take in the last like token or word of the sentence, and then you would like predict the next one.
And at the end, I did like a model that kind of does something similar to an image search. I found a data set, split it into training data set and the validation data set. I tried to like train a CLIP model using the training data set. And the goal is that given a query, it would output the 9 most relevant image from the validation data set. And those 3 are the like I guess the 3 rounds I did it. And the queries are down below. It's not perfect, but it works to some degree, especially the blue one. Half of them isn't really blue, but kind of works.
Right, so we didn't only train a clip model, we also trained just an encoder decoder with language modeling. Basically, we just used a vision transformer for the encoder and just like a normal decoder transformer with cross attention. And here are some of the results. As you can see, it says it gets the baby lamb as a newborn cute lamb on green grass, born cute lamb on green grass. it got young. This is supposed to be Charlie Chaplin wax figure, but it gets young man of love, young man with red and U's on a heart on black background. The author or something. And then the last one. Classified the cat as a dove. And this commercial is actually spelled incorrectly in the data set, so it learned to say chimerical instead of commercial. All right, that's done. Any question? Oh, okay.
Jason, do I need to refresh or are they all? I just refreshed. Do I need to refresh later? Okay.
All right, hey everyone, this is the Privacy Preserving ML Lab. This is a new lab we're running in AI security to explore different ways that we can keep our data private when we're training ML models. And I'll let Max and Lee talk about 3 different techniques we explored throughout the quarter.
So the main problem we wanted to solve is that while AI can be a powerful tool for analyzing large amounts of data, some models are trained on sensitive data like medical or financial information. So we used a variety of attacks like the membership inference attack that can reveal this information. So to preserve privacy, we can use differential privacy to limit the impact of each data point. And then from there, we can train and develop models in a more decentralized manner using federated learning to further protect privacy. So we'll explain what each of these concepts are later on.
The first thing we did was develop a membership inference attack. Essentially, we're trying to determine whether or not a point was like used in the training data. In our like ideal world, the model like perfectly learns everything, and it can like always accurately identify whether something is like we're using like CFAR, so it's like 10 classes trying to identify like what class something like an image belongs to. And in an ideal world, like it sees the image and knows exactly what it does. But like practically, the model that we'll train can like pick up patterns that aren't necessarily in our like testing data. So you might have like more confidence for a point that was used to train the model as opposed to a point that like wasn't. And then he mentioned already that like if you have like financial information or medical information, this could be dangerous because it could be like you could be revealed as being part of like a data set, and then you could have your information leaked. The first thing we did was differential privacy, and we talked about this pretty briefly, but in essence, like you're just adding some degree of noise to like every point. That way, like if I were to add another point, like you couldn't tell whether the analysis, like the difference in the analysis is a result of the noise or if it's like the data point. So you just add the noise, and then I think for us, we added it to gradients because we were just doing gradient descent, and then it was significantly more secure when we tested it than prior.
So another method we used was federated learning, which is basically a decentralized way to build and train machine learning models. So as you can see in these diagrams, normally training will occur on each device, and then the model updates can be aggregated by a central server. So all the information is going to one specific place. But then in federated learning, we can remove the central server entirely and implement more like peer-to-peer learning. So we employed this when we were designing our machine learning models, and yeah. What else?
Yeah.
Thank you guys.
And then we are moving Lux AI up and putting the information in the intermission later.
Please.
Okay, our project was tackling this machine learning competition on Kaggle.com called Lux AI. And the competition is it's kind of hard to explain. I think I'll just like play a video. Yeah. Okay, so essentially you control 16 units. And then around the board there are walls and there's places that restrict your vision. And then the goal is to essentially get to these little golden areas. And if you're on there at a certain point, you'll get points. And then the goal is to have more points than your enemy team. And then you can also sap your enemy team to restrict their energy, and then you get to get more points than them, and then you win. So the initial strategy is, so developing a model for instance is kind of difficult because if you just have a grid and you say I have a unit here, and here are all the features, and then you want the model to output 16 actions. Well, how do you map each unit to each action unless you tell it, this is unit 0, this is unit 1, this is unit 2. So a way to circumvent this problem is let's just use a unit, and then we give it all the features here, and then if it outputs a similar action grid, and then we just see if the unit is on this grid, we take this action from the grid. So the unit is simple by doing this, and then we use a Siamese network to also predict the reward, and then this functions as a PPO sort of model, and we're able to train this PPO. And this is the initial model, right? So the problem is, so this problem is, because you can have multiple units on one grid, you can't actually tell, like the model cannot differentiate which units should do which action. So then if you have two units with like one of them has really high energy and one of them has very low energy, well then you aren't able to say, oh, the higher energy one should go attack and the lower unit energy one should retreat, right? And this is also really messy because you have a 24 by 24 grid and you only have 16 actions, 16 units. So then as a result, most of these outputs aren't actually used. So what's the solution? Well, the solution is very obvious. And like most things, we're just going to use transformers. Okay, so now we use a transformer. Essentially it's the same thing, but instead of just having each unit be on the input map, we also just use the sort of units to query the final output to get, oh, if I have this unit, it's at this position, it has this much energy. Well, according to this output, what should I do with this unit? So then we treat it like sort of a vision transformer where you just convert each grid into like a very long sequence. You flatten it into a very long sequence, and then you just query it to get the final actions. And there's another problem, which is that PPO just doesn't work, and the model doesn't do anything. So what's the solution? The solution is, well, like the problem is that the model doesn't actually ever get to like a point where you can reach rewards, because it's like so hard to move units to where you want it to be so that it can actually get like points. Because you have this whole grid and you can move them anywhere. Well, it's never going to reach a point where it learns that, okay, if I move a unit here, I'll actually get points. So what we can do is we can just train it on a model that already knows how to play the game. So we just copy other people. We just take 500 games from the top 3 players on the leaderboard, and then we just train our model on them. And actually, this is a thing that they give us. Like there's a specific API they give us to let us copy other people's games. So we just do this, and then we're also able to train our reward model, which is actually very useful, because then we can just directly port this to a PPO algorithm and already know like what reward we're expecting to get. And then we have a final problem, which is the model did not learn anything, even though we did this. So you can see here, none of the actions move. I mean, none of the units move. It just sits there. It's not doing anything. And then it moves to the right, and then yeah. And then we're competing against a very simple rule-based agent, by the way. And it ends up getting all the target points, while we get nothing. So that concludes my experimentation. And I think the main issue here is that there's probably just many bugs in the code, because we had to code PPO from scratch, imitation learning from scratch, feature extraction from the actual dictionary they give us from scratch. So yeah. Go on and on.
All right, guys. So I decided to do a different approach. So I got inspired by LLMs. So I was like, I'm gonna make every problem autoregressive no matter what. So yeah, train an autoregressive transformer always a transformer, yeah. On same thing, imitation learning, that's where you copy other people because it saves time. And CNN feature extraction because I didn't want to just flatten all the information. That's step one. Step two is the hard part where you use a Monte Carlo tree search with PPM, which is like kind of similar to PPO, but not. Actually, it's not even. Never mind. Ignore that. So this strategy is from a paper called R Star Math. If you've read it, cool. If you haven't, essentially you simulate multiple different trajectories of your autoregressive like model. Like you sample like the top K possible like outputs, and then like each like output becomes a node, and then you have a tree of all these possible actions, and then you make it play out the game, at least in our case, and then like the winning nodes are rewarded and the losers are like bad. You did bad. No. Okay, so this is the model. This is the game plan. So we have our map information like tile type, like nebula, asteroid, and then you have like the grid of energies on your map. You feed that into a CNN to make it a 1D vector. And then you have your unit positions, like your unit energies, your relic, that's the golden thing that you saw in the video. So you feed that, and then you cat them together, and then you feed it straight into a continuous transformer. And then I do a final linear layer to make it into a 16x3. Actually, I do 16x1, and the other two are, you know what? Wait, you didn't explain this, or? Well, because the units are able to sap or like zap other enemies, like shoot them. And the first dimension is for deciding what action the units do, and the other two are for the position of where to shoot if they do. So that's why you need 3 at the end. So yeah, that's my transformer. So now that we have our model, I have to get the data to make the model imitate. So what Clark did was just pull the games from the top of the leaderboard. I just like decided to just choose one rule-based agent that was pretty good and just like milk it as much as possible. So this cool guy on Kaggle made this thing called Relic Bound. It's a rule-based agent. So I like took his code and then proceed to milk it for like a couple of days. So yeah, I gathered like 50K episodes because like, transformers are very hungry. If you ever checked how much data ChatGPT, DeepSeek, whatever they use, it's a lot because their probability space mathematically is very huge. So they need a lot of data so they don't overfit. So yeah, I just gathered a bunch of episodes of the rule-based agent playing against itself and generated half a terabyte of data and then converted all into the feature that I wanted. Yeah, it was a very annoying process. And if you're wondering if I could have sped it up, no, because he wrote the code and I'm not about to look through like 2,000 lines of code myself. And ChatGPT couldn't either, so yeah, now I have the data now, so I have to train the model to imitate the data. So it was actually working really well. Like the model was improving. I had a very simple pipeline. It had a learning rate scheduler with a warm-up epochs. And yeah, honestly, it was a very weird, the loss was very low, so I was very skeptical. I double-checked my loss function. It was a cross-entropy function, obviously, because you have a bunch of actions and you want to decide which one's the best. So cross-entropy, obviously, it's like a classification problem. Yeah, so it was training really well, and I was skeptical, and I was like, oh my God, I ran the model. It's doing something. So at least, no offense, at least it's better than the last one. It's like actually exploring the map, what it's supposed to do. And then it all goes down shit. Oh, sorry. So after like at step 50, they just stop doing anything. Like the enemy gets 1 point and it just gives up. It stops moving. Like, I don't know where learned this, but I realized, oh yeah, so like these two were just like staying still and there's like a rowing node like right there. Like I don't know how you don't see that. Yeah, so the model learned 2 things. It's to explore in the beginning and at some point to stop moving entirely. So I was wondering, why is this mathematically happening? And it turns out in most of my training data, the actual rule-based agent, all it does is explore in the beginning, and once it lands on a relic node, like the point giving like golden things, it just stops moving because you're getting points from staying there. it's good. But my model, it does that, but it forgets the step where you actually have to go on top of the rogue node to get points. So yeah, but I don't know how to teach that. So I guess there was like a bunch of flaws in my approach. Obviously, there was like one where I don't actually encode which unit is which. But yeah, each training takes like a couple hours, so and I had stuff to do, so unfortunate. But I did get points, so I could have done MCTS there but yeah, I actually didn't. I implemented the entire pipeline from scratch. Yeah, it was very sad. I made sure it worked with LLM, so I know it should work, but I never got to test it. So yeah, you can't really, like Clark said, for PPO or any like these type of like RL training, you need like a sufficient baseline, and my baseline wasn't sufficient by definition. So yeah, I spent a long time optimizing the code because MCTS or any sort of like those kind of algorithms is very extensive. Like you have to, in expanding a tree, it gets pretty deep because if our game is 500 steps, like think about it, each step 20 children, it gets pretty big. The trees expansion like takes like a couple minutes, and let's say I want like 50K trees, then that's gonna take a very long time. So yeah, I had to optimize code and it took a long time. I did try before getting a baseline, but it didn't learn because there's just no reward to learn on. So yeah, my bad, guys.
Okay, everyone, we're gonna take a break for food, but before you get up to get food, make sure to scan the QR code and fill out the form. Additionally, since we got chicken sandwiches and mac and cheese, we're gonna have the vegetarians go first so they can get all their mac and cheese before, like, just so we know it doesn't run out. So yeah.
Also, for the vegetarians, there's one tray of non-vegetarian mac and cheese. Do not get the one with the little pink bits in it. Thank you.
Don't worry. Next quarter,
Leftovers, you can go back and get leftovers, and we're gonna have a line form over here so they can walk this way.
And if the place run out, it's like the cops, you don't.
So like, you know what? Honestly, all this would happen. Well, it's not that. Yeah. Did anyone have a mac and cheese on it was actually I was not gonna stop using it. And I was right. The entire time. It was just Wait, so you guys are trying to look at
I was looking at Uno. Wait, plus there's no way that like I didn't want to like say this in the channel. There's no way that you guys are gonna try to like say this like you're like that's gonna be like different models. Yeah, this guy's like yeah. Oh, thank you. Yeah. 13
It don't scare me like wait, I just yeah, I'm terrible at play, but yeah, the moment
It's hard. Okay, it wasn't hard. It was like data I'm not gonna do that.
There's a classroom now. There's like this random book. I was like talking about like oh great. This is very complex. Yeah, this is how you get. I mean, please. Oh no, my computer doing things. Yeah. No, like just saying. And as long as the 3.3 volts fan is clean enough, he does the rest of the board could also be throwing noise on the. We need to be like a little meta about this, right? Like, what is like an attack that's like CMU has that no other school has?
It must be a house.
Could it be voltage glitching?
Because I thought you told me that they had voltage glitching at that time.
No, you did voltage glitching.
Wait. You said that CMU did it, so then now we're gonna get.
Why would CMU be a desk?
No, or they had voltage glitching for ECP.
No, I never said that.
No, no one did it.
Who
last
told
year.
me that?
No, no one did it. No, you're
Oh,
kidding.
okay.
No one
Yeah,
did it.
maybe I hallucinated it. There is a rumor, like generated rumor that they have.
I mean, we had the same board. They could have spent a whole year R&Ding it, right?
Yeah, I mean, they might have done that because they don't do knowledge yet.
Yeah, I feel like Sig Tony would have gotten any like software attacks. You know what I mean?
Yeah. Yes. Just it's like you don't know the values, but the thing was like no, for example, you might be able to you can use that as some basic knowledge. With that, most of their code might not be pre-accepted.
But also, like, the thing about the cyber is I don't catch it. Oh, it's actually matter.
Yeah.
They're like our sites good like in the time chase like oh, those are shirts though. They're not sweatshirts. Like I really like something. That's the meeting is when we make man on the show. You can be able to hack it and see log patrol is one of those like really escalation things. Or sorry, not for it's one of those exploitation things. Hopefully that's like it might be a lot of effort, but like the test is like you can somehow just like because you're it's like a bunch of generics that are being like that's
All right, I'm gonna try beating it at 1.5. You're going so. Also, I now realize I can't learn. Yeah, and also like an hour, like, you say, we're not gonna like. Yeah, they're like. Yeah, but we're not like taking our entire time out of that these days. I just do it. It's like one of these sometimes. Okay, well, this is not that much. Yeah, that's right. These are not scam people. I don't know if they know like that's like I'll try. Why? Everything is this. Like I don't mind there is I had like it's like I don't know I would pretty much I don't pretty in the open folder and then like I went Sometimes we just have actual all for first sandwiches. Yeah, when you like like there's two sandwiches left. We're not for like the first time ever we're not taking home like trades of food. Actually, there's the more plates and cups are used in the trays. Wait, we're gonna go fries? I don't like fries. Oh, I guess they'll run out of fries.
Wait, I ordered 3 trays of fries, so I didn't imagine that the fried trays were so small. That's probably why they were cheap. Well, I say cheap, but the 3 trays of fries cost like $100.
Can I random tax a fry from anybody?
It's like blocked by the
Just one, I need to know.
That way they can force it.
For the
It's like, what tray of mac and cheese costs like $80? Yeah, it's so cheap. It costs for like double.
This was like
Yeah, Panda all comes like Panda's like super cheap. Yeah, but we're doing Panda first idea, so I didn't want to do Panda. But like Panda catering is like really
Are there any other fast food places?
Wait, most places Taco Bell.
I don't think I found that. Go.
I'll let
Do you know he was?
No, like people actually need to pay. Yeah, we can update that ACM
We'll start up in a couple of minutes. So engineering 1 is the next one up. So just get ready for those who are presenting.
Yeah, if you're presenting for E1 and you're done eating, please like come to the front.
Please get it. Fuck me down here tonight because I probably everything Cyber does from now to the end, which is really funny. And let me get down here. Ready? Remember, you have 5 minutes. So okay, go. Are you ready? Should we start?
All right, everyone, we're starting the presentations again.
Okay, yeah, everyone. Hopefully you enjoyed your food. We actually had exactly enough chicken sandwiches, Lamau. But I want to say just before we start that, like, please keep your presentation to exactly 5 minutes or like less, because like the second half of our presentation actually has like much more content. Like I think twice as much content as the first half. So Yeah, please go. Please actually keep it at 5 minutes. Anyways, without further ado, Anthony, you should get up here. We will next be presenting our E1 class, E1A malware defense, which is led by me and Anthony here this quarter. So E1A malware defense is a class where you learn Python and kind of build a malware that has like a client and a command and control system. So without further ado, we'll let people present this. So introduce yourselves as well.
I'm Nicholas.
I'm Chloe. I'm Reva. Chaya.
Oh yeah, you guys stand close to the mic and also like press the button.
Okay, so when we're talking about collecting information from a target machine, we do that by using a technique called enumeration. So one way we can do enumeration is by port scanning. We can do that through the TCP. So it's a connection-oriented protocol which establishes a reliable connection for sending data. And this happens by a three-way handshake. So first we'll send data with a synchronized packet or synchronized packet. And then if it's open, then the server responds with a SYNAC, so synchronize acknowledge. And if it's closed, then the server responds with a reset packet. So here's an example of that. And something to note is some firewalls block responses, making port secure filtered. There's another type of port scanner you can do, the UDP. And this is connectionless, so there's no handshake, and packets are sent kind of just forgotten. If there's no response, then the port is likely open. And then if you receive a ICMP or port unreachable message, the port is closed. And so here's an example of that. And then this example uses Scapy, but you can use like Nmap or just Python to automate scanning.
So exploitation is the process of using known vulnerabilities to gain access to your target machine. One way that my group did this was we used a bash vulnerability, which allows remote attackers to execute arbitrary commands. So basically it puts the commands that it wants to execute into a specially crafted HTTP request. So here you can see a picture of the code. Essentially, it splits up what the attacker sends into arguments. These arguments are joined into commands, and then the commands get put into this variable, this really long variable that is basically the HTTP request. And then it runs that. This one. Privilege escalation is the process of gaining higher level access and permissions. So not everyone can do everything on a computer. You need special permissions. And this is the process of getting those permissions. So one way we did this was through SUID abuse. Basically, if the SUID bit is set, that allows anyone to execute that file with the permissions of the file owner. So now we could execute it with the file owner privileges. This example basically does that for Python, but you could also do it for Shadow, which contains all the passwords. So if you set the SUID bit of that, you could theoretically change the passwords of the target machine.
Okay, so I'll explain command and control. So this is the process of communicating with the target to retrieve data. So that might be something like some groups did keystroke logging, or basically sending a command to receive back information that the target likely wouldn't want you to have. So here is a different command that we implemented, which is playing an audio file on the target machine. So the attacker can send a audio file from the attacking machine, and with the code that we've placed on the target machine, when it receives an audio file, it will play that upon receiving it. And we also implemented a screenshot attack. So when the capture image attack is sent to the victim machine, it will take a screenshot, encode it as a byte string, send it back to the attacking machine, which will decode it and download it onto the attacking machine so we can see the victim's screen at any given time.
So persistence, so this means we already have in this case, we have malware already on the target machine. We want to make sure it stays there, and even if if someone does something to it, it'll keep going. So first thing I did was for my group was a systemd service, which basically says I want systemd to execute the script on startup, and then if it ever gets killed, wait like a minute and then bring it back. So even if the user kills this our malware, it'll come back every single time. And then also I did this I wrote a small script for alias hijacking, which means I can basically write some code that says whenever the user types cd, ls, pwd, or cat or anything like common shell commands, it'll do the thing, but then also execute some malware to make sure that the malware is always running in the background. It also does some weird obfuscates this alias application, so it looks really weird and complicated when it's actually not doing much. So yeah, even whenever a user types in one of those things, it'll be run by malware.
And finally, we want to be able to kill it, so we don't get caught, hopefully. So the way my group did this is through it, the script was essentially a monitor that for the existence of a certain YouTube video, and if the YouTube video was deleted, it would delete all traces of the malware on the machine. So it would delete any changes any like persistence things that we did to make it keep going, and it would also delete the payload, which is what runs on the target machine. And that's it.
Thanks. Thanks.
Yeah, I can talk about that.
All right, hello everyone. We're from ACM AI. We're the two officers who led the diffusion project. Unfortunately, none of our group members could make it tonight, so we're going to kind of talk through the process that we went through this quarter. We'll start by going through kind of what is diffusion. You'll hear about it a lot, both in image generation and now in language modeling. Diffusion is a process used for generating images and other videos, as well as more discrete data forms. Essentially, you can use a combination of Gaussian distributions to add noise to an image, and then train a neural network to iteratively remove noise from that image. And once you train that network, you can essentially apply that network to pure noise, given some context, to get a completely new sample, a completely new image.
What we did was we trained the diffusion model on a data set of 10 million images for about 200 epochs. The architecture we used was very similar to Stable Diffusion 3, which you can see here. Our version was an inferior version of this. It was smaller and we removed some features, but it was similar enough. And here are our results. On the right or on the left, this is supposed to be a tree, and you can see that this is some form of plant life, with the exception of the orange one. And on the right, this is some kind of animal. You might think it's a dog, but it's actually a cat. I don't think our diffusion model ever figured out what a cat was. Yeah. Thank you.
DVR, come down. Anyways, I hope you don't miss me because I'm presenting for the rest of everything Cyber does today. But anyways, while people get down here, DVR is ACM Cyber's competitive CTF team. If you don't know what a CTF is, it's a capture the flag competition. You basically have teams basically host remote binaries or remote web servers that are vulnerable on some remote service, and you just pwn them and get flags. It's pretty fun. So DVR highlights this quarter. For the first time ever, we hit #1 in the US. our team for doing that. We could not have done it with all of you guys. We are unfortunately now third in the US, but hey, that's still pretty good. And we had some pretty fire results at External and CTF. We almost made finals. We didn't quite make it. And then we also played U of T CTF, TRX CTF, and Calabar CTF. So those were all pretty fun. And without Oh yeah. Something else we did this quarter, our biggest event this quarter, so arguably Cyber's biggest event, is we ran something called LACTF, which I don't know if you guys have heard of. It's our own cybersecurity competition, and it's our third time running it. We had over 1,000 registered teams. We had 55 challengers, 10 sponsors, and 6,000 K in sponsorships. We had 30 high schoolers visiting in person from I think like Valencia High School and like a couple other places. And we have over 10,000 flags submitted to the platform. So massive thanks to our 20 plus organizers, all the people in this room. Huge shout out to you guys. All massive thanks to our challenge authors, to our volunteers, and also like we also did actually became the third largest UCLA Discord server for like a couple of days, so that was pretty cool. If you care about that.
We are right now still.
We are still.
We are still.
But yeah, we're gonna highlight a cool challenge from LACTF. This was, I believe, the hardest web challenge, Giga Chess Space by Rodak.
Yeah, so this is the hardest web challenge at LACTF and something that I wrote. So I guess the background for this whole challenge. So there's this thing, okay, it's called chess space, and the gist of what it does is that it lets you as a chess player learn opening theory. The way it works is like you just like search for openings, then it like gives you more info. But I made this, but chess base costs too much money. I can't afford that, so I made this thing called chess base. And what this does is that it does the same thing, you know, I type in my opening, it searches the database. I don't see what the difference is between these two. Anyways, so yeah, so the gist of the challenge is that there's a premium opening, and this premium opening is the flag that we're trying to get, and only the admin has the premium membership, so only the admin can get this. And we have to trick the admin into giving us this opening. So just as an aside, like this is how normal web challenges work. So this is a web security challenge. This is how they usually work. So you typically try to find a vulnerability in the page, allowing you to inject HTML, JavaScript, or CSS into there. And then if you can do that, you can take control of the page, because if you can put JavaScript on the page, like JavaScript is code, you can do whatever you want. And then after that, you get flag, you send it back to yourself, and you're pretty happy. So now we're gonna dive into the application, and let's see if you guys can spot the vulnerability. So this is the high level flow of the application. There's two softwares, the front end, which runs on your browser, and the back end, which is the API that the front end is like sending requests to. So the way it works is that the front end gets the search query from the URL. Like if you've been to Google and like put in a search result in there, if you see like they have that weird question mark Q equals query. So like the front end gets the query from that. The next step, the front end asks the back end for the opening matching the query. Then the back end sends a matching query and the front end displays it. And in addition to this, the page has like a ton of like random security stuff enabled, like CSP referred checks. So can anyone see the vulnerability in this? There's no direct vulnerability in this. I've misled you all. Okay, so this might seem kind of hopeless as a challenge, right? If there's no direct vulnerability, how are we going to get the admin to give us a flag? Well, there are these things called side channels. So the gist of a side channel is that like, while there isn't a direct vulnerability in something, like what we can do is that we can trick the application into just exposing information through like various side effects that it does. And the gist of how to exploit these side channel attacks is that we make something called an oracle, which it just tells us whether a search succeeds or not. And then like using this sort of algorithm, like if we can get a search succeed function, we can exfiltrate like an entire text. Like we can just like see if LACD is in the text, if LACTE is in the text, and then if something else is in the text, and we can just keep iterating this to eventually get a flag. But the search succeed oracle is the main gist of like, there's a main challenge. Like, how do we get this oracle? So one key observation that we make for websites is that like while tabs are like sandbox from each other in the browser, there are certain resources that are shared, and one resource is a connection pool.
So sending requests requires opening a TCP connection to the backend and sending and receiving some request text. And like to prevent your computer from like dying, your browser limits the amount of connections to 256. So it turns out that we can actually use this to time requests on another tab. So for context, like this is what the flow would usually look like. We have our page, we can make requests, and there's the admin page. They can make their requests. And we can't get any info on this. But using this connection pool, what we can do is that we can first hang 255 connections. This means that now instead of 256 connections, the browser just has one connection left. Now, after we hang that, what happens is that since there's only one connection left, this has to execute in serial order. So now all of a sudden, we force this thing to execute one after another, and we can use subtraction to figure out like this time. So that's pretty cool. We can time requests on other sites. The second key observation is that if you looked at the fine print earlier, a successful response is a redirect. So if you know how networking works, it turns out that like redirects actually take 2 times longer because the way they work is that the server sends you a redirect response and then your browser makes another request. So redirects take 2 times longer and we can time requests on another site. Putting these all together, we're able to get this Oracle search succeed because we can just time the requests on the other site using this connection pool technique. So I guess to wrap up, the final solve to this challenge, you first open the ChessBase, you send the admin a website which opens ChessBase in a new tab. Your website hangs 255 connections, and then you make your Oracle search succeed, and then you use that technique I described earlier to just build up to a flag. And yeah, that's chess-based.
ECTF people, get up here.
So yeah, this quarter, some of us in collaboration with IEEE, we competed in this competition called Embedded CTF. And so yeah, I'll have some of our officers talk about what we did.
Yeah. So our competition scenario for ECTF this year, and note that ECTF every year is like kind of a different idea. This year, our task is to design and implement a satellite TV system that kind of securely encodes and decodes TV data while also protecting against unauthorized access. So what do we mean by that? What do we mean by that? We have an encoder that's written in Python, and then we have a decoder that is actually written in bare metal C, and that is running on a literal firmware board. So in terms of our encoder just takes in like a channel number, a timestamp, a TV frame, and some amount of global secrets that we can supply. And then we get to run an algorithm on that and then generate kind of an encoded frame. And then on the decoder, we have to support 3 kind of operations. We have to support listing channels, so like what channels are we subscribed to for this TV program? We have to be able to update subscriptions, so like, hey, you're now subscribed to channel 3, thanks for paying us. And also decoding frames, which is kind of the most important thing, like actually displaying frames to the television. And we have to do all of this securely without letting adversaries be able to say read pirated channels or like buffer overflow and like destroy our board.
Okay, so that's the functional requirements, but we need to protect against malicious actors. So these are the attack scenarios provided to us in the competition that we need to defend against. A lot of them fall in the same category of the subscriptions. The idea that you should be able to read a subscription that you don't own anymore, but previously did, or that you've never owned, in the first place. And then there's also a special type of scenario where you're like someone's neighbor and you're trying to mess with them a little. So you keep sending data to their satellite or their decoder. And, ideally this shouldn't interfere with them, but in an insecure device, it could.
So to make this secure, one thing that you have to consider that makes everything secure is cryptography. So how are we going to ensure that nobody except the encoder can send actual subscription updates, so no one can pirate subscriptions? We can use signatures for that to ensure that the encoder is the one that's actually sending subscription updates. But how do you ensure that subscription updates only work for the device they're meant for? So device A gets a subscription, device B can't pirate it from A. So that means that you need to encrypt the entire subscription package with a specific key that depends on the secret salt and the decoder's ID. And then how do you encrypt the actual TV frames such that they only work within the actual timestamp, the time range of the subscription? So we could use one key for every timestamp, but that would be a lot of keys because the timestamp is like a 64-bit integer.
So we need to compress this a lot. So we have this thing called the key ratcheting algorithm. So for key ratcheting, we kind of compress 64-bit ranges into like 128 keys at most. And the way we do that is we kind of like take a prefix and we hash it using SHA-256. And then depending on like whether a bit of the prefix is 0 or 1, we either select the left or the right half of the hash for our next key.
So what exactly does the encoder do? The encoder generates subscription update packets and creates up to 128 prefix keys to give access during the timestamp duration. Then it also generates an encryption key, encrypts, signs, and sends a package over to the encoder. So for encrypting a frame, we use key ratcheting to determine the key for the timestamp. And then, yeah, we encrypt frame, sign, and read, send. So then for our decoder functionality, it takes in the encoder values and we try to process it. So to process the frame, we have to verify the frame signature. We don't want to take any invalid frames. We determine the key used to encrypt the frames using key ratcheting, and we decrypt the frame and output it. And then to update a decoder subscription, we verify the encoder's signature, encrypt the subscription package, and we persist the subscription to the encoder's flash. And we hope this does not get hacked.
Yep. So when we were making our design, everything was working fine, and then we realized that we can't just like take like infinite time to like do everything. So for example, you need to be able to send more than 640 bytes per second when you're sending TV frames. So obviously the solution is to overclock our device, and that actually did work. So cool. And then we also need to make sure that when we're sending some subscription update packages, we need to send them in less than 500 milliseconds. So initially we're using 32-byte keys for our encryption, but most of the time was being spent on like transmitting these keys over UART. So we just reduced the size by half to 16 bytes and then fixed some stuff in other places, and that met the requirements as well.
And yeah, I think that's all. Thanks, everyone.
Do I just exit and okay, cool. Hi, I'm Maxine, and I'm going to talk a little bit about the AI reading groups that we do. So, reading group is the thing that we do on Saturdays, and we either have someone come and give a talk about like research they're doing or something cool that they learned about AI, or we get together and read a paper together. So this quarter we did 4. So I'm going to go and give a high-level overview of what we learned about in each one. So the first one we did was on DeepSeek R1 by Artine. Shout out Artine. He flew in from the Bay Area and willingly gave us talks, a shout out. We talked about techniques like mixture of experts, and speculative coding, which is a technique used at inference time to improve to speed up LLMs. And then Jordan led us through a talk about the analytic theory of creativity in diffusion models. So we talked about why diffusion models, or we talked about a paper that explores like why we think diffusion models are creative. Apparently, according to the theory, like diffusion models like should really just like overfit on like the training data and just give us like exactly the set of images that it was trained on. But this paper showed some interesting things about how they think that like when you train a diffusion model, it's actually like trying to match like each patch of the image to like stuff from the training sample, but it's doing it across like different images and different like parts of each image. So that's where it gets that like creative aspect and is able to generate variations in its image. And then it does like a cool replication thing where it shows that its theory method is very similar to what you get with actual diffusion. So very cool paper there. And yeah, we also talked about compressing LLMs for efficient inference. So the high level idea of compression here is that LLMs these days have like billions and billions of parameters. And if we just use like 32 bits to represent every parameter, well, then we'd need like gigabytes and gigabytes of like RAM, and no. Well, wouldn't it be cool if we use less memory? Yeah, so that's the idea of just trying to reduce the cost of inference by just like using less bits to represent your parameters. So we talked about cool things there. And we also talked about AlphaFold, which, I mean, Google's coming out with like AlphaFold. They did AlphaFold 2. It's very cool. We talked about some whatever is going on here, some interesting biology things and some specialized, they have like a special take on their transformer called the Evo former that they use for this biology stuff. So there's some cool things there. Yeah, if anyone's interested, check out the reading group channel on the AI Discord. Thanks to everyone who came out to reading groups this quarter. And shout out to Ben from Cerritos who brought donuts to our last reading group. Yeah, that's it from me.
Cool. Yeah, I'm going to talk about the GPU cluster that I think probably a lot of people here are using. I'm from AI safety, but this is a collaboration between us and ACM AI. And so it's not just people from ACM AI I think are using this. I think there's some people in cyber who are also using the server.
ETF is powered by your server.
Really? Great. That's perfect. That's what I like to hear. So who am I? I'm Christopher Milan. I'm president of AI safety at UCLA. I spent a significant amount of my time this year building out these servers. And also the shift between dimensions of these slides was not kind. And so therefore, if you want to look at the slides again, maybe you want to go visit my URL there. And you can view them again online if there's anything you find interesting. And so what's the talk about? While setting up and administrating these servers, there's plenty of interesting challenges. Right now, I'm going to talk mostly about how we chose our hardware. But there's also our blog aisafety@ucla.org, which has plenty of other interesting stuff about that we learned throughout building these servers, and we'll continue to learn as we continue to administrate them. Here's this cool graph that I made of the topology. I think I'm just going to kind of skim over this because I don't want to take too much time. Basically, the important thing is we have 4 servers. They're all connected through CSNet. One of them, Sullivan, is our login node. And then we have 3 other servers, which each have 3090s. So there's 4 3090s on 2 of them and 5 3090s on another one. Those are all our GPU servers. And I'm going to talk specifically about them. There's some interesting stuff about the login node too, but you should probably check out our blog if you want to learn more about that. The first question is, why did we use the CPU that we use? So we used AMD EPYC Rome, which is AMD's sort of Zen 2 server CPUs. These are 2 generations old now, I think, because they skipped 4, but now there's like 5 and 5C, but 5 and 5C are like kind of the same thing, but not really. So we can call it 2 generations old. And so one of the important aspects here is the memory bandwidth. Obviously, I think if anyone's tried to run a large language model locally, this is like one of the most important factors. It actually doesn't really matter at this point as much how fast, how many flops you have, but rather how quickly you can get all these parameters in and out of your model, because we have these ridiculously large models, right? Like we were just talking about DeepSeek R1, which is what, like almost a terabyte of, or sorry, almost it's way more than a terabyte, but anyway, whatever. Another thing that's nice about it is this one of the CPUs that we have, this 7532, is only $200 on eBay, and that's a 32 core, 64 thread CPU, like 3 gigahertz. Like apparently x86 processors are pretty solved at this point, because you can get that for only $200, which seems pretty crazy to me. But really the killer aspect of the CPU is the fact that it has 128 PCIe 4 lanes. Since we're using 3090s, we're on PCIe 4. If you look at alternative processors here, you certainly can't use something off the shelf. Like you can't go down to Micro Center and grab like a Intel i5, whatever. This is not going to have 128 PCIe lanes. That's not going to happen. You're going to maybe have 32 or something like this. So that's a very important factor. As we can see on on the motherboard we end up choosing, you can look at it like this is a ridiculous CPU. I mean, look how big that CPU socket is compared to like what you would normally see in your average computer. But also importantly, you can see all 7 PCIe lanes there. I put a little note there about how slot number 2 has a ghost living inside of it, but we'll talk about that in a second. At the time, this was a very reasonably priced server board. Right now, it's gotten really, really popular. If you Google like how to build like a GPU server, everyone talks about this board. And so when we bought it, it was not super expensive, but now I think it's gone way up in price. And I don't even know if ASRock still makes them, so that's probably related. And also, a lot of them were coming from China. I don't know if you can buy stuff from China anymore, so I don't know what's going on with that. The other thing you'll notice, and this is kind of even more a pressing concern, is if you ever seen a 3090, like they're huge, like they're ridiculously wide. You can't plug them all in right there. Like look how close those slots are together. That's not going to work. So, we have to come up with a solution for this, right? As it turns out, crypto miners have this exact same problem. And so, you can use PCIe risers, right? And, so this is a photo of Temescal. I took it earlier today. Surely nothing could go wrong with this, right? Like it looks fine. Like, everything's plugged in. You can't see the GPUs; they're cut off at the top, but everything's plugged in up there. Who could foresee any sort of problems with this? Well, as it turns out, there actually are plenty of errors. As soon as you plug all this stuff in, you grab whatever cheapest risers you could find on Amazon, you plug everything in, and you turn on your computer and you boot into Linux, and all of a sudden you see this streaming down the screen at you. And if you look really carefully, if you have really good eyes, then maybe you can see this. It's full of little errors that say, oh, like communication error on PCI. And the problem here is signal integrity. So if anyone's taken CS 118, they'll talk about this, and you do like symbol interference. But anyway, the point is, like, you're introducing a ton of noise, and we're going to get back to the demons inside slot number 2 to learn more about this. So let's try to understand how this works. So this is the block diagram for the motherboard we're talking about. And so that big thing up there is the CPU. And then there's all these little peripherals. So let's zoom in and look at the PCIe slots. So here's PCIe slots 3 through 7. I don't know why they're numbered like that. They're in the wrong order. But anyway, all of these are directly connected to pins on the CPU. So that's part of the reason that CPU socket that we looked at earlier is so massive, is because it has a ton of little pins on it. And the reason you get to have so many PCIe lanes is because you want to connect directly to all these pins. And all these are directly connected. You don't see PCIe 2 here because we look at PCIe 2, it's got all this huge mess, right? And the reason it's like this, if you look really carefully, you can see, oh, it has like all these little switches, and you can configure the motherboard to allow you oh, well, I want an extra M.2 drive, like I want to put another SSD in there, or I have an Oculink card, I want to plug that in, or I have an extra SATA drive, I need to plug that thing in. And so being able to set this all this up, it allows for additional configuration. But you'll notice that even if you plug a GPU directly into slot number 2, you may experience having these AER errors without even worrying about like any sort of riser. And that's because every time you introduce something like this, you're introducing signal loss. And this is exactly what the risers do as well. And so this is an issue. And it turns out there's also another issue with risers. It's the fact that these PCIe devices draw power both from the power supply and the PCIe bus itself. I don't know why they designed it like this. I mean, it's probably because in the way olden times they didn't worry about drawing power from the power supply directly. This ends up being an issue because if you think about it, you have 350 watts each TDP for each of these 3090s. Some of them are even higher. Like if you buy like one from MSI, they bumped it up to 400. It doesn't affect the performance whatsoever, but they just make it draw more power. If you multiply that by 6, you're getting 2,000 watts. Like you can't plug that into the wall. Like that's not going to work. And so the solution is you buy 2 power supplies and you plug them in 2 different outlets. This is not going to work because you have 2 power supplies and they're both trying to power two different rails at the same time. And both of them, you're going to blow up 2 power supplies. They're both trying to power the same rail at the same time. They're both trying to assert 12 volts on the same rail at the same time. They're going to start fighting with each other. One of them's going to think it's slightly above. One's going to think it's slightly below. It's going to be some sort of horrible hysteresis loop, and you're going to just destroy your power supply or trip the breaker and bolt her, and we don't want to do that. The solution to this, you might think, oh, well, we can just like tape off the little PCIe slot power connector, right? You can look up a pinout for this, and you can just put like a little bit of Kapton tape over the slot. This doesn't work. I tried doing this. I tried taping over the card edge and just like blocking off those pins. The card fails to be recognized. So that's not going to work. So we actually do need to come up with a solution here. Right now we only have 5 GPUs plugged into at most to one of the machines, but we want to buy more GPUs. It seems reasonable that we'd want to figure this out. And even like 5 times 350 plus everything else you have to plug in, like you have your CPU, you have all this other stuff. Like this is probably going to be too much. So an option is you just ignore it. You have fewer GPUs and you just deal with the fact that the sometimes you have AER errors. This is really annoying. If you ever try and communicate data between the GPU and the CPU, that means half the time your message is not going to be transmitted and it's not going to work, right? Like if you're trying to communicate data and half the time the data doesn't go through, your throughput's going to be half. This is not a good solution. We did it for a while actually, but it was not great. The other thing is you could buy better risers, but you still have to have fewer GPUs, right? You still have to run into this power problem because the risers do communicate the 12 volts over that. And also, we actually did buy some quite high quality risers. There's this guy on, he had a blog post about how to do this. And he went through it and says oh, you should buy these risers, you buy these risers. We tried buying those risers and it fixed some of the problems. It didn't fix all the problems. So the question is what did the pros do? And so the way they do this is they actually use the SIM/connectors, which are these little things right here. And like you use those instead. And instead of using I think these are twin axial cables or something like this, something that reduces signal integrity loss. And so you have to use these. So as it turns out, like really that motherboard that we said was so great, it was actually not that great. We should have bought something that had a bunch of some size connectors in it. But now if you ever want to build your own server, that you should buy something like this. So that's kind of all I have to talk about there. But if you're interested in learning more about that sort of stuff, you should check out our blog. I'm also going to give a very quick pitch about AI safety. I'm going to tell you first the way I'm going to tell you about this. I'm going to tell you about a little story about the summer research project at Dartmouth. So I'm going to read through. I know this is a quote. I shouldn't read off my slides, but I'm going to read off my slides. And so the idea here is we proposed a study on the basis of the conjecture that every aspect of machine learning or every other intelligence can in principle be described such that a machine can be made to simulate, right? And an attempt will be made to find out how machines use language, form abstractions and concepts, solve kinds of problems now reserved for humans, and improve themselves. Right, and I cut this out of the quote, but they're proposing to have like a group of like 10 people over the summer study this and figure out these problems. And we think that a significant advance can be made if a carefully selected group of scientists work together for a summer, right? As it turns out, this is from 1955. This is a plan in 1956, the summer of 1956, to study AI and to solve these problems. Obviously, this didn't work. They didn't. It took a little bit more than a summer. As it turns out, solving problems like these requires a lot more trial and error than you were expecting. And people really thought this was going to be super simple. Like they really these are smart people. And if you read their proposal, you read the whole thing. It doesn't read like it's totally goofy. It doesn't read like they're out of their minds. Like they totally didn't understand how complicated. They didn't understand how complicated this problem was. But it reads as if they were well thinking out this problem, and yet they still completely believe that they would be able to solve this problem in a couple months. That took it's been like 60 years, and we're starting to scratch the surface of these problems. And so because of this, I'm going to introduce another problem, which we are sort of principally concerned about with the AI safety, which is the alignment problem. And the formulation of this goes that for a sufficiently advanced system, ensuring its goals are the same as ours is a non-trivial task. And I'm not going to talk about this for too long. So if you're interested in learning more about like how this problem propagates, you can look up universal paperclips or something like this. It stands to reason that alignment will be similarly difficult and will require similar, given that our approach right now it requires a lot of trial and error, and we constantly try one thing to see if it works, we try something else to see if it works. If we wanted to solve a problem like this, that would take a long time. But the problem with with alignment is we only get one try, right? Like we built some crazy super smart intelligent system, and we failed to solve alignment. And it's not aligned with our goals, it's game over. And if you're interested in hearing more about why this is the case, you should join our club. And what to do about that. But I hope that this is somewhat convincing that this is an issue that you should be worried about. So you may be interested in joining us. Our website is ais-ucla.org. So programs we run we have an Intro to AI Safety Fellowship. You can read about those also on our website. We also run upskilling tracks. So this quarter we taught about CUDA. They wrote a kernel, matrix multiplication kernel that competed with cuBLAS. So if you want to learn everything from the ground up about how to write matrix multiplication that's about as fast as cuBLAS is, you should check that out. Will also runs a reading group. You can ask him about that, and server access, you can ask me. Obviously, let's talk about the server. And yeah, that's it.
Roger made it back.
Yeah.
All right. It's been a full year. It's been really a great honor being your co-president. I guess for both cyber and AI. But it's time for us to move on. So, I just wanted to say thank you all for being so amazing and for showing up to our meetings. I don't know if any of you.
Really great thoughts. Yeah.
Oh yeah, I've been so thankful to be the co-president for Cyber because Cyber is a really great club, and I don't know, you all make it so fun. So thank you all.
We say some things. Yeah, maybe we should say some things. Yeah, thanks to everyone I met in ACM AI, to all officers and all the general members. It's really great. So fun, tremendous year, went by so fast, but yeah, really grateful for everyone. Thanks for coming out today, and yeah, hope to see everyone around. I'm not like dying or anything. Yeah, hope to see everyone around.
Yeah, same thing for me, really. Thank you guys so much for the opportunity. I'm really happy with where the club's gone to in the past year, and really looking forward to seeing where our new leadership takes us from there.
Yeah, and we'd like to welcome the new C presidents for AI and Cyber.
Great, so you start. Hello, it's Joshua and I will be the new C presidents for Cyber. I don't know if you want to say anything, but I'm really excited to be the C pres for Cyber. I love how the club has been going. I really enjoy like going to all the cyber meetings for the past 3 years or so, and I'm excited to continue all the great work we've been doing in the club, maybe expand the club and improve it incrementally for the next year or so.
Yeah, we do a lot of cool stuff. Let's keep doing cool stuff.
Hi everyone, I'm Selena. I'm going to be ACM AI president next year. I really enjoyed being in ACM AI, starting off as an intern last year and a workshops officer this year. And I'm really excited for next year. Thank you everyone.
Okay, thank you all for coming. As usual, before you all go, we would like to get a picture. So if you all could come down here, we can take a picture.
Wait, Jason, can you grab that at the table?
I can just take it, but I want to.
Just block the fire alarm.
It's reachable.
Anyone?
It's still recording. Yeah, it still is. Do you want to stop? Stop it? Sure.